Okay, so the point that we left off for Chapter 16, because Chapter 16, one of the things that it's been trying to get us to focus on, first of all, sense organs. Those little free nerve endings, the little corpuscles, the different types of ways that we're receiving the stimuli. So if you remember, we have been talking about what we see as our general senses, and those were the ones that were like the free nerve endings, the corpuscles, and now that we have moved into the special senses, we kind of talked about taste, smell, with taste having those taste buds and the little taste hairs that are on those, and then for the sense of smell, having that chemical, which was an odorant, basically dissolve in the mucus of the membrane, mucus of the nose and so forth. And then for hearing, because that's the one that we left off, for hearing, how did we have the stimulus reach the hearing?
The entire process.
Yeah. Well, the airwaves. Okay, remember it's on the waves. They come in, hit the tympanic membrane. All right. Then we got the little ear ossicles that are going to move. And then we begin to go into that inner ear, and we're dependent upon the fluid that was in that cochlea. Now remember, the vestibular cochlear nerve branches. We have the one part that goes to the vestibule, the other half goes to, well, not going to say half, the other branch goes to the cochlea. Do you happen to remember the two fluids?
Perilymph and endolymph.
Perilymph, endolymph. Endolymph, if we were to take that cochlea, unroll it, it would look like we would have 3 rows that exist in it. The 2 outer ones have the peri, the middle has the endo. What else was located there?
What was its name? It's the tactile.
The tectorial membrane. And we had those little cilia, the cells, the cilia pushing up into that. Now remember, for any of the stimuli that we receive, we have to turn it into an impulse that the brain can understand. The only thing that it can understand is going to be the chemicals. So we have to create an action potential. And that action potential, when we have a stimulus, for example, the waves coming into the eardrum, they have to be converted to a chemical message. In the tectorial membrane, do you happen to remember what electrolyte was important? My potassium. Now, the structure of those cilia, they looked like they were in stair steps, and they contained tip links. They were basically, looked like they have the string running between the 4. When the tectorial membrane is pushed upon by the waves from the perilymph, okay, it causes those tip links to bend. When they bend, our electrolytes, the potassium, get to pass across the membrane. If you think back to a plasma membrane, having those pluses and minuses move across the membrane. Do you guys remember the repolarization, depolarization, hyperpolarization? Okay, if you remember, when we begin to change that electricity across the membrane, we generate the action potential. If we do that, that action potential gets to make it to the area of the brain that can interpret that stimulus. So when we think about hearing and we think about where the cochlea is located, we're going to move to an area within the temporal lobe. The other part of the inner ear was the semicircular duct. Let me think here for a second. That is termed the vestibular apparatus. That is going to have the vestibular nerve coming into it. Now, the structure of this apparatus, it's going to look something like this. All right? There's a reason for that. Can you think of why we might have one pointing up, one pointing down, one to the side?
Because those are all the directions that we may be flip around. Or...
Those are the directions we might be moving. Equilibrium. What does that mean? In balance. It's going to be my place in space. The structure's pretty cool. We're going to end up with some really cool terms, all right? Somebody got very inventive in lab that day. We're going to have two chambers. Anterior is called the saccule. Posterior, the utricle. Like I said, if y'all know, like, where this might, or anyway, okay. When we talk about equilibrium, we have two types. We have equilibrium that is static. Static means pretty much not moving. All right? So static, the type of equilibrium it's going to pick up on, what is my place in space for my head? My head, is it pointing up? Is it pointing down? Is it going to the side? Okay? Dynamic means the body or something in motion. So, what is the motion of my body? We have linear. What's linear mean? In a line. Lines can go up and down. They can go side to side. What do you notice? I got up, down. I've got side to side. But I can also, with my body, not me, personally. But some can and just flip, okay? Backwards, over, all right? All this different types of movement. Why does my body, why would I need a special sense for equilibrium?
Maintain balance when you can't see.
I gotta maintain balance. I gotta make sure I don't fall over.
But like when you're, so like standing upright and is when your body is probably gonna operate like at its optimal level. So if you're upside down, your blood's not gonna flow properly. If you're side to side, your blood's gonna, like the rest of your body. So in order for your body to get back to the proper place, you have to be in an upright position so that it can work properly.
Good. Yeah, excellent. I like that. Because you've got to think about how the other organs in my body might be affected by being upside down or side to side or something like that. You know, it's like children, and you know how kids are, if they're kind of like, you know, little daredevils and stuff, they like for the parents to maybe throw them up in the air or, you know, maybe toss them on the bed or hold them upside down, you know, or something like that, okay? And it's so funny because when I was growing up, if my parents or my grandparents or something saw somebody doing that, they would be, oh, mercy, they need to help that child. They're going to flip that child's liver. You know, that's the type of stuff I would hear. Because I guess they, even though in not fully understanding everything, I guess they were thinking, okay, if they're being held upside down like this, their organs were going to turn upside down. In reality, okay, what is happening is an effect on blood flow. So there is an effect to blood flow when the body is not, and I like the term that Brian used, in the optimum position. Upright. You know? So with equilibrium, our body has to make sure that it can adjust to the different positions we put it in and different positions that we really, I mean, it has to happen. For example, riding in an elevator, moving in a car. You know, you've got these movements that take you up, down, side to side, front, back, okay? Now, the way that it's going to do this, we got to come back to our chambers that we're going to find with those semicircs. We've got the anterior, the posterior, my saccule, my utricle. In these areas, in these chambers that we're going to see being present, they're going to have cells. Once again, we're going to refer to them as the hair cells, and because these are going to be nerve cells, all right, nerve cells always have supporting cells to help with their getting of nutrients, getting rid of waste, that sort of thing. That those patches that we're going to find in each of the chambers are referred to as macula. So that little patch of cells that I'm going to see in the anterior and the posterior, the term for those is macula. I will have one anterior, I'll have one posterior. One is for my vertical movement, one is for my horizontal. Does that make sense? There they are.